Welcome to Lecture 2 for Math 239. We're going to start today by talking about counting subsets. If S is an n-element set, we've already seen a formula for the number of subsets of S. It's just 2 to the n. We've also seen a formula for the number of length k partial lists of S. That's n factorial over n minus k factorial. Both of those questions are related to, but they don't actually answer the question of how many subsets there are of S of a given size. Suppose k is some integer between 0 and the size of S, and I want to know the number of k-element subsets of S. I will be giving you a formula for this pretty soon, but it's actually convenient for now to give some notation for it even before we know how to compute it. If n and k are any non-negative integers, we write n over k, almost looking like a vector as you'd see in linear algebra, to denote the number of k-element subsets of an n-element set S. Now we don't say this like a vector. The way we say this is n choose k, because it's the number of ways of choosing k elements from a possible n if we don't care about the order. Now even if I haven't given you a formula to compute this, it's easy to figure out what it is in certain examples. For instance, for any n at least 0, n choose 0 and n choose n are both going to be equal to 1. And that's simply true because if I have an n-element set, it will have exactly one 0-element subset, the empty set, and it will have exactly one n-element subset, the set itself. Similarly, it's not hard to figure out what n choose 1 should be. If I have an n-element set, then n choose 1 is the number of 1-element subsets of that set, which is of course the same as the number of elements, namely n. So n choose 1 is always equal to n. Finally, I didn't actually say in the definition that k needed to be at most n. If k is bigger than n, then clearly an n-element set has no k-element subsets, but that's fine. We allow the notation to take care of that. We say that if k is bigger than n, then n choose k is 0. Note that the statement above that n choose 1 is n, that's also true when n is 0, because there's no 1-element subsets of the empty set. The first real theorem we'll prove is one that can be used to compute n choose k for any n and k. Here it is. N choose k is equal to n factorial over k factorial n minus k factorial. Now this formula actually breaks if k is bigger than n because you get negative factorials, but if k is bigger than n, you already knew that n choose k is 0, so that's fine. Now the way this proof is going to go is by relating k-element subsets of S to length k partial lists of S. Clearly these are closely related notions already. A partial list consists of k elements of S where we do care about the order. A k-element subset consists of k elements of S where we don't care about the order. And we can use this relationship and the fact that we know something about the number of partial lists to figure out the number of k-element subsets. So just to remind you, the number of partial lists of length k in S is n factorial over n minus k factorial. We're going to compute the same number in a different way. To tell you a length k partial list of S, I could just tell you its elements in order, but instead I could tell you a length k partial list in S by first telling you the subset of S that consists of the elements of that list, and then telling you the order of the elements in that subset. In other words, I can describe a length k partial list of S by specifying a k-element subset X of S, and specifying a list of the elements of X. These two choices are combined using AND, which means that the number of partial lists of S is equal to the number of k-element subsets of S times the number of lists of a k-element subset of S. Both these things are things we know, at least we know the notation for the number of k-element subsets of S, that's n choose k, and we know the number of lists of a k-element set, that's k factorial. Therefore, the number of k-element partial lists of S is n choose k times k factorial. But we also know that the number of length k partial lists of S is n factorial over n minus k factorial. These two formulas look different, but they must be the same because they're both the number of partial lists. So we can write down an equality saying n factorial over n minus k factorial equals n choose k times k factorial, and we can just rearrange that by dividing through by k factorial to get a formula for n choose k, which is what we wanted to prove. This technique, where we show that two quantities are equal by counting the same thing in two different ways, is known as double counting. This is a genuinely new method of proving that two quantities are equal, and it'll give us a way to prove many different combinatorial formulas. It's very important in combinatorial enumeration in general. Here's another formula we can prove using double counting. If n is a non-negative integer, then n choose 0 plus n choose 1, and so on, up to n choose n is equal to 2 to the n. This will be a short proof, and I'd encourage you to pause at the moment to see if you can see how it's going to go before you continue. The observation to make is that both the right-hand side and left-hand side of this formula are ways to count the number of subsets of an n-element set. For the right-hand side, this is just something that we saw last lecture, where we showed that the number of subsets of an n-element set is simply 2 to the n. For the left-hand side, we can think of it as a formula for the number of ways to choose a subset of S, where we divide up according to the size of the subset we're going to choose. Choosing a subset of S is the same as choosing either a 0-element subset, or a 1-element subset, and so on, or an n-element subset. We know that there are n choose 0, 0-element subsets, n choose 1, 1-element subsets, and so on. We're combining these choices using OR, so to figure out the number of possibilities, we simply add these numbers, n choose 0 plus n choose 1, and so on, up to n choose n. And that's a proof. The right-hand side is equal to the left-hand side because they both count the same thing, the number of subsets of an n-element set. I like this example because it really points to the power of these ideas. We proved this not by interpreting the left-hand side and the right-hand side as algebraic expressions that have formulas that we can manipulate, but instead by interpreting them in terms of their meaning. The meaning of 2 to the n in this proof was the number of subsets of an n-element set. It was not the product of 2 by itself n times, which is more an algebraic meaning of 2 to the n. Now from the previous example, we do actually have formulas for n choose 0, n choose 1, up to n choose n, and so on. And we could in fact prove this identity by applying these formulas to the left-hand side and then using induction on n. However, I don't like that proof, and nor would most mathematicians. It's not only messier, but also it doesn't answer the question as to why the identity is true, as well as my original proof. This is the difference between a combinatorial proof, which is one like the one I gave, and an algebraic proof, which is one like the one I didn't. Both types of proof certainly have their place, but in many cases a combinatorial proof is seen as the gold standard. And if you're asked to prove a formula, it often makes sense to look at the expressions in the formula and see if you can understand the meaning of those expressions in terms of counting objects of one type or another. If we explicitly ask you for a combinatorial proof, then this is what we want you to do. In many cases, a combinatorial proof of something is possible, even if there's no easy proof by double counting. I'm going to give an example of this, and before I prove the example, I'll talk about how we might try to prove it, and then use that to give a definition which will be really vital for combinatorial proofs. Here's the example. If k and n are integers at least 1, then n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Before I proceed, I'll mention that you can find a short algebraic proof of this identity by simply using the formula we have for n choose k and doing some manipulations. However, that algebraic proof won't answer the question of why it's true, as well as the combinatorial proof that we'll be finding. Since we have both n choose k and n minus 1 choose k in this identity, it makes sense to talk about an n-element set and an n minus 1 element set. Let's say S is the set 1 up to n, and S primed is the set 1 up to n minus 1. This will allow us to give a combinatorial meaning to both the left-hand side and the right-hand side of the formula. Now, the left-hand side, that's n choose k, so that's simply the number of k element subsets of S. The right-hand side is the sum of two different terms. The first term is the number of k element subsets of S primed, and the second term is the number of k minus 1 element subsets of S primed. So together, the right-hand side is the number of subsets of S primed that have size k or k minus 1. Now we can't just use double counting here, as we did in the last two examples, because double counting only works when the left-hand side and the right-hand side are both counting exactly the same thing. Here, the left-hand side is counting subsets of S, the right-hand side is counting subsets of S primed, and those aren't the same thing. However, it's enough to show that the objects being counted on the left-hand side and the objects being counted on the right-hand side can be paired up with each other. I'll show you what I mean. The oval on the left represents the set of all k-element subsets of S. The pink dots in the oval represent the subsets themselves. So the number of pink dots on the left is equal to the left-hand side, n choose k. On the right, the two smaller pink ovals represent the two terms on the right-hand side. The top one is the set of all k-element subsets of S primed, and the bottom is the set of all k-1 element subsets of S primed. Because we define them this way, the right-hand side of the formula is the size of the union of these two smaller collections. To show that the left-hand side is equal to the right-hand side in the formula, it will be enough to show that the large pink oval on the left and the large pink oval on the right have the same number of elements. And for that, it will be enough to pair up the elements on the left with the elements on the right. Here's an example of what's happening when k is 2 and n is 5. So on the left, I've got all the 2 element subsets of 1, 2, 3, 4, 5, and on the right, I have all the 1 and 2 element subsets of 1, 2, 3, 4. Now, because this is just a small example, we could easily observe that there's 10 things on the left and 10 things on the right, and we could put them into correspondence any way we liked. However, what we're looking for is a natural way to associate the things on the right with the things on the left in a way that will generalize to other values of n and k. Now, I may have written the positions of these elements to make this a little bit easier, but hopefully you can see a reasonably natural way to associate the things on the left with the things on the right. The 2 element sets like 1, 2, which do not contain the element 5 on the left, are also elements of the right. So 1, 2 is on the left, 1, 2 is on the right. We could try putting them in correspondence. The same for 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So we've paired up 6 elements on the left with 6 elements on the right in a reasonable way. This leaves us with 4 elements on each side to pair up. But there's also a reasonable way to do this. It makes sense to pair 1, 5 with 1, 2, 5 with 2, 3, 5 with 3, and 4, 5 with 4. Now, if you were asked to describe this rule in general, it wouldn't be too hard to work out what you're doing. For each set x on the left-hand side, you'll associate x with the set x itself if x does not contain 5, and you'll associate x with the set you get by removing 5 from x if x does contain 5. Now, this is just a rule we came up with in one case, but it turned out to be the right rule to work in general. If I forget the case where k equals 2 and n equals 5, and I just think about the general case, then the left-hand side is the set of all k element subsets of S, the right-hand side is the k or k-1 element subsets of S primed. And if I just replace the 5s in my rule with n's, I get a rule that will allow me to associate things on the left with things on the right in a way that pairs them off perfectly, and it works for arbitrary n and k. In general, this rule will map sets on the left that do contain the element n to smaller sets, to k-1 element sets on the right that don't contain n, and it will map sets that don't contain n on the left to themselves, to k element sets on the right. This rule will put sets on the left and sets on the right into one-to-one correspondence, and it follows from that that the number of sets on the left is equal to the number of sets on the right. In other words, the left-hand side equals the right-hand side in our original formula. Now, what I've said there essentially is a proof, but it'll be convenient when looking at more complicated arguments like this to have more mathematical language to talk about these things. For this, we need the definition of a bijection, which is just a rule that pairs elements in one set A uniquely with elements in another set B. Formally, we say a bijection between two sets A and B is a function f from A to B, such that for all pairs of elements in A, little a and little a primed, if f of A equals f of A primed, then A equals A primed. In more technical language, this is saying the function is injective. The second rule is that for all little b in the set B, there exists little a in the set A such that f of little a equals b. That's saying that the function is surjective. Together, they make that the function is bijective, and a bijection is just a rule that uniquely associates each element of A with an element of B. You might have seen this definition before when talking about functions from the reals to the reals or similar, but in fact bijections make sense between any pair of sets. In this course, to prove something is a bijection, we'll usually be using a simpler rule, which says that a function has a bijection if and only if it has an inverse function. If f is a function from a to b, then a function g from b to a is an inverse of f if for all little a in the set A, we have g of f of little a is equal to a, and for all b in the set B, we have f of g of b is equal to b. In other words, the function g and the function f undo each other. Why do we care about bijections? Well, the reason is because if we have two finite sets A and B, and we can exhibit a bijection between them, f, then f pairs the elements of A uniquely with those in B, and it follows that A and B have the same size. Of course, A needs to be a finite set, or equivalently, B needs to be a finite set for this to make sense. In this course, we'll be handling finite sets. There's a nice piece of notation in the notes to indicate that two sets are in bijection. This isn't completely standard, but in this course it'll be convenient to use. If two sets are in bijection, we write A, forwards arrow, backwards arrow, B, as you can see on this slide. So let's go back to our example and use a bijection to prove that n choose k is always equal to n minus 1 choose k plus n minus 1 choose k minus 1. As before, we'll set S to be the set 1 up to n, and S prime to be the set 1 up to n minus 1. And this time we're going to define the sets A and B that we're going to build a bijection between. A is the set that the left-hand side is counting, the collection of k element subsets of S, and B is the set that the right-hand side is counting, the collection of subsets of S primed that have k minus 1 or k elements. So the size of A is n choose k, and the size of B is n minus 1 choose k plus n minus 1 choose k minus 1, simply by the definition of n choose k. It's enough, therefore, to prove that A is in bijection with B, because that would imply that they have the same size, so the left-hand side is equal to the right-hand side. To prove that there's a bijection between these two sets, it's enough to find a function f from A to B and a function g from B to A, so that g is the inverse function of f. And we already know the right rule to put elements in A in correspondence with elements of B, now we just need to write it down. The bijection f from A to B is going to be the function where f of x is equal to the set x itself, if x does not contain the element n, and it will be equal to x minus the element n, if x does contain the element n. To give the inverse function of f, the question we're asking is how I would undo the function f. In other words, if I took a set x, applied f to it to get a set y, what would I do to get from y back to x? A moment's thought will tell you that to get from y back to x, the answer is to do nothing if y has size k, and to add the element n back if y has size k minus 1, because the only way I could have obtained a k minus 1 element set by applying my function is if the original set x contained n, which was removed. In practice, if you have a function f that you think is a bijection, it should be relatively easy to state what the inverse of f is. If you have trouble figuring out what the inverse of a function should be, it's a sign that perhaps that function isn't actually a bijection. Now technically, to prove that f is a bijection here, we would need to prove that f and g are inverse functions of each other, not just to state the values of f and g as we have. However, I'm just going to claim this without proof, and in general when you're solving problems like this, we're happy if you just state without proof that these functions are inverses, provided you've defined the functions f and g and the sets a and b correctly. So, contingent on my statement that f and g are inverses, we know that f is a bijection, therefore the sets a and b are in bijection and therefore have the same size. This was enough because we know that the size of A is by definition the left-hand side of our original formula and the size of B is the right-hand side, so we've proved the formula. Now this formula that we've just proved is probably the most famous one that relates quantities of the form n choose k. In fact, we can use this formula together with the fact that we know what n choose 0 and n choose n are to compute n choose k recursively, at least in principle. For example, say I want to know what 6 choose 3 is. By the formula, that's 5 choose 3 plus 5 choose 2. 5 choose 3 is 4 choose 3 plus 4 choose 2. 5 choose 2 is 4 choose 2 plus 4 choose 1. Now we could go down further than this, but we could just compute these exhaustively at this point, and I've done that here. 4 choose 3 is 4, 4 choose 2 is 6, 4 choose 2 is 6, 4 choose 1 is 4, which gives us 20. In fact, if we arrange the expressions of the form n choose k in a triangle as I've done on the left, with 0 choose 0 at the top, and so on, then this formula is saying that every entry in the triangle is the sum of the two entries above it. We can use this to very quickly fill out the triangle, and the fact that 6 choose 3 is 20 can be seen at the very bottom of the triangle on the right. This diagram is known as Pascal's triangle, but in fact dates back to centuries before Pascal himself. Thank you for watching. Next lecture we'll see some more examples of nice combinatorial proofs and bijections.